thank you for joining us on Isifundi Training and our new three-part Bite-Sized Corrosion series, where we're going to be spending some time looking at the corrosion protection of marine infrastructure. My name is Vanessa Seeley-Fisher, and it is my great pleasure to host you today. In every session of Bite-Sized Corrosion, we try to break down another aspect of corrosion-related information into what we hope is interesting and informative and palatable nuggets of information, so that this will help you to make your own corrosion experience easier to digest. So we do hope that by the end of today, you'll be leaving us having learned something new and very eager to continue your journey in understanding corrosion a little more. Now, in this series, we're going to be spending some time getting a little more information about some of the corrosion challenges associated with marine structures. And I'm really delighted to welcome Frances Bradfield of Ramble to our microphone today. Now, Frances is not an unfamiliar face on Bite-Sized Corrosion, and in fact, she shared some of her experiences with designing corrosion protection systems for offshore wind farms in our Maritime Corrosion series last year. So if you missed it, or you'd like to refresh your memory, we'll put the link below. So Frances, welcome back, and thank you for joining us.
Thanks, Vanessa. I think this is actually our fifth session. We did ECDA on pipelines as well before this.
Talking about ECDA, I wanted to expand on our conversation from last time on wind farms, but before we get there, I wondered if you've got any observations about differences that you've found you've had to take into account when you've looked at offshore corrosion compared with dealing with corrosion of onshore buried structures.
Again, I was a pipeline girl at heart, well, I am still, and I was working on onshore pipelines before I moved 5 years ago to the offshore industry. And it was a very steep learning curve for me because in general, especially in South Africa, of course, everything's rather dry. Unless you're currently in Cape Town, which I think is probably quite wet. And you obviously have much more dry conditions and something slightly easier to manage than the turbulent offshore conditions that we can expect. So I really had to learn, a whole lot of other restraints that we didn't know we needed. For example, environmental issues where we can't just go around having tons and tons of metal dissolving into the ocean, for example, as well as more difficult access issues that we might have. When you're 70 or 80 kilometers offshore versus 70 or 80 kilometers into farmland, it's a little bit more tricky to do tests and checks and maintenance if we need to, not least if we need to go to the seafloor to do that. So we have got a lot of dissimilarities in the environment, but of course, a lot of it carries over from what we know from onshore corrosion protection to offshore. At the end of the day, it's still metal, it still rusts, and we need to keep the electrons inside somehow.
I can imagine that some of the other challenges that you deal with are temperature influenced. We're dealing with a very stable temperature when you're buried onshore, but offshore, I imagine that there's quite a lot of fluctuation, and that also has an impact.
You're absolutely correct. I think not least if you start thinking about weird geothermal or other kind of seismic activity that might happen if you're on the seafloor. We, of course, have vertical differences in temperature. So if we're dealing with any kind of marine structure that goes through more than, say, 10 meters of water, you have quite a large stratification of temperature going, obviously, in summer from the hottest temperature at the top to cooler, more stable water lower down. And in winter, you actually see the opposite effect, where you can have frozen water, ice, and even ice effects on your structure, which, if you can imagine, isn't great for the coating that you may have on your structure, to slightly warmer water at lower elevations. And I'm sure you've spoken before, but of course, this temperature differential changes your current requirements. And if you have differences within the same structure, that's also an issue that we have to look at.
And last time you were telling us, when we were looking at wind farms in particular, you were indicating how you're constrained geographically on your structure where you can put your anodes, and right, having to disseminate your current in the different requirements across the depth of 70 or so meters. That to me seems somewhat challenging.
Yeah, it's extremely challenging. And I think the way it helped me a little bit in the beginning was to think of something like a monopile, a vertical offshore structure, just as a lying down pipe standing up. And we can talk about the offshore pipelines in a minute, but you would expect the conditions to be very uniform on a pipeline of 70 meters lying down. But as I said, it's completely not going the other way. And so, yes, to get the different current requirements at the different elevations of your structure is challenging depending on what your structure looks like. For some marine structures, for example, sheet pilings or more jacket-like structures, sort of telephone, the big telephone mast looking things that go in the water, you can distribute galvanic anodes very nicely so that you have more anodes near the top where you have a higher current demand because there's more oxygen and higher temperatures, and fewer lower down, or vice versa, depending on what you're designing for. That's great. But as soon as you have something that needs to be transported and smashed into the ground, like a monopile, you are restricted to having anodes only in one location. And that does give large design constraints, which is something you don't see on a pipeline offshore, but you could liken it to a single point deep well ground bed for an onshore pipeline, where you have to take into account the distance and how far we can get the spread of the current along the pipeline. Similarly, the distance we can get from the structure and the depth to which we can achieve protection along that pipeline.
Yes.
Vertically.
It is interesting to me that obviously we're land-based mammals, and so our context is usually land-based. And when we start thinking offshore, we have so many additional parameters that need to be taken into account, which can cause so many challenges. And I find that fascinating within the CP sector, particularly because of this, how do we distribute the current within the constraints of the geography of what we're looking at. But it's also interesting that you describe it as this kind of vertical pipeline, because that does help one to picture it a little bit better and determine how it works out. Now, another thing that you mentioned briefly in our discussion last year was the differences between structures that are permanently installed in a set place and floating structures. Now, that's also something very different from the land-based scenarios where everything is fixed. And my imagination of floating structures is you let them go and they start off in Denmark waters and they end up in the Pacific because that's where we want the holiday. Obviously, they're not completely floating. They're obviously floating by design, but stabilized in some form. Do they stay there forever? Do they bring them in? And does that impact the way one puts cathodic protection onto them?
Yes, that's a very good question. And the first thing I thought about is, how is this going to work when I heard of the first demonstrator? So offshore wind floating is a very new technology. It's still in its infancy with a lot of conceptual designs and what they call demonstrators, where they take a 1 in 10 scale and make it so that they can prove of concept for investors or certification bodies, governments, etc., that this is okay. The first thing that we've got to realize is the scale of these things. The new current wind turbines that are being produced are tip to tip for the rotor 250 meters. To get the scale of that, it is halfway around a running track, a little bit more actually. It is a significant distance.
Yeah.
So now if you imagine that is now at least 300 meters tall at the center of this pinwheel that you've got, you have a huge surface area that is being blown and generating electricity at any one time. So the structures themselves of these floating structures are enormous, about 200 meters per pontoon. So you've got, for example, 3, they are either triangular or in 4s, and you've got these huge 200-meter triangles going across like this with massive pontoons in the middle and on the sides, with pontoons diameter of 12 or 13 meters across, which they then use as ballasting tanks. So this makes an incredibly difficult thing when they come to me and say, so we're just going to put anodes on it, right? And I think, yeah, okay, 200 meters of 13-meter diameter, that's a huge surface area, times 3, plus the complicated geometry of the pontoon in the middle, and then usually, obviously, something to hold the whole wind turbine up on. It makes it very challenging for us to do. To answer your earlier question, actually, they are stayed to their final locations with anchors of some type, either normal drag anchors or sometimes actually drill into rocks and have tendons coming down. And those also need to be protected depending on what they're made of. But the largest issue that we have is how to protect the internal, where we have ballasting water coming in and out, and how to protect the external, which is where we have basically a ship moving up and down with waves that splash around. And as we know, that is the most harsh section of any kind of offshore foundation. I think we could always ask ourselves, why don't we just do what we do on ships?
Yes.
that was my first thought. I'm like, well, we do it on ships all the time. We have huge Titanic style, massive ships, and we send them out, which are probably at least 200 meters long, similar kind of surface area, etc. And then I started getting into the use cases of this. And this is to answer your question, Vanessa. When we say they're floating, they're not fixed, but they are there for lifetimes of 25 to 30 years, where
Okay.
they will drag them out, plunk them in the middle of the ocean, and leave them for 25 years. And this is how they make their business cases work. So we need to try and come up with a way to protect these with as little maintenance as possible for 25 years. So the challenges are not dissimilar from those of a fixed bottom foundation. We have very unique issues in that if we use impressed current anodes, those lifetimes are short. So you would
Hmm.
need to come up with a way of changing them every like 15 years or so. That's at least one change out within the lifetime. And then also we have to start looking at what happens when our coating degrades. On a ship, that's not a problem because we
Comes
dry
into dry
dock
bulk.
them every 5 years, which means we can inspect them and we can make sure that we have no issue with the shields that stop the protection from becoming too high near the anodes, which has got an issue with structural steel. But on a fixed floating foundation, we do not have that option because that coating or those anodes that we put out there need to last for as long as we can. It's very, very challenging.
If you say they're still at concept stage, the advantage of that is that you can still play for a little bit before it becomes critical. Do you see that this is kind of the future of where these are going, that they'll rather do that than the monopiles or the fixed permanent structures?
So floating has the advantage that you have, it sounds like a lot, but you have less steel when you go into extremely deep waters. For example,
Okay.
in Norway, we have fjords, which are mountains going down to tiny valleys, and they want to put these foundations in the very deep waters, 500 meters deep is what we're
Wow.
talking about. So where we can go maximum depth for a monopile is 75, 80 meters. So that's the
Mhm.
upright pipeline. Of course, you can
Yeah.
imagine the longer that becomes, the more wobbly it becomes, the more difficult it is. So we
Yeah.
can't go infinitely long there. We can have the same volume of steel with really long tendons
There's,
or chains or whatever they are to connect to the bottom. And that then makes deep water offshore wind or deep water platforms way more feasible than their fixed bottom companions.
Now, I know nothing about oil wells and offshore drilling and so on, but I imagine that they have gone through some of what you are experiencing now with wind has been forerun, as it were, in the petrochemical sector. Do they also use floating platforms there for the same reasons?
So not to my knowledge. It is possible that they do somewhere in very deep waters that they would do that, but the issues are in that case would be very different because the weight and the loads that they are putting on these structures are much lower. You do not have a 300-meter monstrosity on top of your platform trying to push it over. You have maybe a platform with a small topside and a drilling or pumping rig. I'm not in offshore oil and gas at this stage. I've done some pipeline work, but to answer the question, it wouldn't be as challenging. Your
Yes.
structures would be smaller, I think.
And I'd forgotten already about the concept that you've got this huge, effectively sail, which is designed to be a sail because that's how we're trapping the wind energy. But all the constraints that must be from an engineering perspective are really quite interesting, just how they are designing the structure to be strong enough to withstand the wind that they're trying to harness.
Exactly. And light enough so that we don't waste a whole lot of steel. So it really is a huge optimization puzzle.
Yes.
And it's very exciting that especially corrosion engineers get to be a part of this because keeping the material as low as possible is something we can assist with, but also making sure that that material stays fresh for as long as possible means that the lifetime of these structures really increases. And so I would say that it's obviously, I think it's the most sustainable discipline within engineering is corrosion protection and coatings application to make sure that we can have good structures in especially in renewables.
Yes. Well, that doesn't make sense if renewables are are not looking after the very structures that they are using to harness the renewables. Absolutely. Gosh, it's a fascinating topic that one could go into, and it's interesting to see how this need for energy throughout the world is driving us to look for ways to get it in places we would never have considered before. And that's also quite exciting to explore new opportunities. I think that's really interesting. And it'll be interesting to see where they go and how you take it there. I want us to change tack completely, Frances. Still staying in the offshore environment, but something that you mentioned in your last discussion with us that we said, oh, we should talk about this more, and then we didn't because we ran out of time. So here's our opportunity. And that is something that's become, I've seen a little bit of a buzzword related with offshore and offshore corrosion protection. That is accelerated low water corrosion, or the acronym being ALWC, and just trying to define a little bit better what it is, where we find it, and where that is influencing corrosion protection and our strategies in terms of maritime structures.
Yeah, so that is a good question. And I always say it's one of these mystical black boxes. We have the accelerated low water corrosion, and then we have this mythical beast called MIC, or microbial influenced corrosion, which is where you have little bugs that eat into your steel. I think sometimes these things are used quite, maybe even interchangeably in some instances, but they are linked very closely. And it's very interesting to see the approach taken in different sectors of the marine environment. For example, I think the standard approach, and of course, jump in if I'm wrong, Vanessa, but the standard approach within marine, so ports, harbors, whatever, is to consider accelerated low water corrosion as that small area kind of below main water level where we have like a tidal movement, and or close to the mudline where we have differential oxygen or more organic matter, less organic matter. And my understanding of this is that it comes closer to shore. It's a more near shore phenomenon.
Right. Yes.
I think when we get further offshore, and depending on who you're speaking to, so looking into the standards for offshore wind specifically, or offshore foundations, deep water, we start hearing more about MIC and not accelerated low water corrosion. And it is less to do about this upper splash zone, so in between the mean water and the above and the below, so where you would expect there to be a lot of oxygen differential cell here, and more within the upper buried zone, so from the first meter above the seabed to 2 to 3 meters below the seabed. And this is what we call the area of elevated MIC risk. And the reason why I say that is because nobody has found any active microbial corrosion in sufficiently protected structures. So if we have a functioning cathodic protection system, there is no anecdotal evidence from site that we know of. That's at least been reported to the industry, so who knows, that there has been MIC attack on a structure. So some of the Norwegian standards say that if you've got cathodic protection on your structure to polarize to 800 millivolts with respect to silver chloride, so I think it's about 850 with regard to copper sulfate, if my brain remembers correctly from all those years ago, then we are completely fine, and we don't see there as an elevated risk. Whereas some of the other standards, specifically ports, harbors, and one of the new ISO standards still says that they don't know enough. And so they would prefer us to polarize more akin to what we have on onshore pipelines, but to 900 millivolts. So it would be akin to 950 copper sulfate reference electrode onshore. So it's a big black box. And to be honest, I say you can never rule it out. You can always do the tests. You'll probably always find that there is MIC, bacteria at least. So I advise clients to check for the food that they require. So sulfates, sulfites, organic matter. And then we can look at that and say, well, there's none of that. So we're probably fine with 800 or 850, you know. Whereas if we're in an estuary of a river with a lot of organic matter, we can start thinking we're going to see something more like what we see in ports and marine with this accelerated low water corrosion.
It's so interesting, and I agree with you that I think the terms are used interchangeably, and I'm not sure that's correct. And we'll see if we can explore it further at another stage. But it is so interesting that we forget that there are microbes that can do damage. And in the onshore environment, a lot of people are familiar with sulfate-reducing bacteria, and knowing that there are bugs out there in the ocean that we don't know about that could be doing damage. And I think that's also part of this new risk philosophy that is permeating every facet of life and obviously influences corrosion protection decisions, is that there's so much we don't know. Sometimes we have to take an educated or a wise guess about what we think might be there and try to ensure that we protect against, as you say, this big ghostly unknown in case, because the ramifications of us getting it wrong can be so catastrophic. And I think that's also one of the difficulties with these designs, is that we're thinking about, if it goes wrong, well, worst case scenario, what is the loss of life? Then what is the financial damage, the reputational damage, and all of those? And I think those are considerations that we can't play with lightly. We do need to take cognizance of them.
For sure.
Then one last question that popped up as I was reviewing what we discussed last time, and again, in a completely different direction. When you were talking about driving in the monopiles, you were talking about driving in these hollow tubes.
Yeah.
And if you're driving in a hollow tube, you're going to get water on the inside as well as the outside.
Yeah.
The cathodic protection only protects what it sees. We know that. And we know that you've put this fancy superstructure in that's dropping your anodes in close proximity and protecting the externals. What are you doing about the inside of these monopiles?
Excellent question. Actually, what we know that we have water inside, and I think it's important to notice that before, let's say 15 years ago, we made some mistakes in the industry by assuming that this water would become sufficiently oxygen deprived and we would not have corrosion on the inside of the structures. We've learned our lesson, put it that way, remembering that in order to get the cables for the offshore in, we actually have holes in the monopile, which have got cables. And while it doesn't allow a lot of water in, it's sufficient amounts of oxygen to cause significant corrosion. And we've had some problems. Luckily, that was before I was in the industry, so I take no responsibility for it. But what we do is within these big hollow pipes, we have a section that is above an airtight platform. Basically, we lower something down like a stopper, a wine cork.
Yeah.
And then we have a little bit of an air gap and some water below. And from this airtight platform, we hang anodes. We either hang galvanic anodes on a long string like a necklace, or we hang individual ICCP anodes 1 meter in length, about that big and very skinny. They weigh very little. They're great. You just lower them down through the hatch. Galvanic anodes can become more problematic. I've seen designs up to 40 tons, depending on what size the monopile is. So, of course, that gives some primary steel constraints. But long story short, there will be some combination of coating and cathodic protection on the inside of these monopiles because we've learned very expensive school fees is what I think we would call it. Extremely expensive. So
yeah. Oh yeah, I'm sure. I didn't realize that the internal of the monopile was also coated.
Depending, it can be fully coated, or we just coat the welds sometimes, because those are the fatigue critical items. If we're doing impress current, you have some time before the wind turbine produces electricity. So you have maybe a year and a half where it's free corroding within this environment. And depending on the design, we cannot allow for any corrosion on those welds. So it depends on the strategy.
Gosh, there's so much to think about, so much to talk about. And when we're talking about marine infrastructure, it's becoming more complex. I guess as we run out of land space, we have to look at the oceans to provide us with place to either extend with piers and jetties, and we'll talk more about that next week, or generate our electricity in places where we wouldn't normally inhabit. And all of these have got corrosion ramifications which need to be considered. And it's definitely an area that I think will become of increasing importance. And I think we're going to find our oceans filling up with various mechanisms for either capturing solar or wind or both to try and keep the power requirements of our ever increasingly power hungry population, world population, suitably powered up. Frances, thank you. Thank you for taking time out of your day to spend time chatting with us. Thank you for sharing again and contributing to our understanding of some of the corrosion challenges associated with marine infrastructure and getting to grips with some of the terminology. And I do hope that our audience have been as informed and entertained as I have. So thank you for giving us so much food for thought in how to combat corrosion. So thank you for your time.
Thank you, Vanessa.